So a common thing for you to be asked to do in an exam is to sketch some inequalities on an Argand diagram. So we're going to start off by just drawing the loci that we looked at in the previous video and then turning these into inequalities. The first one that we've got here is a circle. So it's modulus of z something equals a number. So this is a circle. First thing we need to do is rewrite this as modulus of z minus 2 equals 4. So this is a circle centered on minus 2i down here. And it's got radius 4, so this will go past the origin, it will go through the real axis. You should be using compasses to draw these. And looking ahead to my inequality, I've got a strictly greater than inequality, so I am going to use a dotted line this time for this one. It's a circle centered on 2. Dotted lines, something like that. We're going to label up on the imaginary axis where this crosses just because it's easy to do so. So my scale's a bit off, but it crosses at 2 and minus 6. Now we're being asked to shade the region here satisfying this inequality. So first off, we've drawn the locus, and then we're looking for basically all of the points where the distance from minus 2i is greater than 4. So in this case, these are the points outside the circle. We're going to label this up with an R. So this is the region that we do want. So we're shading the region that we do want, and it's this outside bit here. If you are ever unsure on any of these questions, you can test a point in your locus to see whether it fits or not. So for example, an easy point to test here would be the origin. If you test 0, 0, so put z is 0 in here, you've got modulus of 2i. Modulus of 2i is just 2. Is that greater than 4? Well, no, it isn't. So the inside bit is the bit we don't want. It's the outside bit that we do want. Next up, we've got an argument locus. So this is a half line. Again, it needs rewriting as arg z minus 2i equals 2 pi over 3. So we're starting again at minus 2 on the imaginary axis. We're doing an angle 2 pi over 3 with the positive horizontal from minus 2. So that's an obtuse angle because pi over 3 is 60, so 2 pi over 3 is 120. It's got obtuse angle. We're going to use a ruler to draw this one. And again, looking ahead to what I want, I've got a less than or equal to and greater than or equal to sign. So I'm going to use a solid line this time. This asks me to shade the region satisfying arg z plus 2i is in between 0 and 2 pi over 3. This is asking for all of the complex numbers starting at 2i, minus 2i, sorry, that have an argument in between 0 and 2 pi over 3. So it's this bit. Oops. This bit in between these two lines here. I am going to make the horizontal a solid line as well. So we're going in between this one and this one, and so I'm just going to shade this like this. This is the bit that we do want. So arguments in between 0 and 2 pi. Finally, for this one, this is a perpendicular bisector. It's modulus on either side of the equation. And this is in the form that I want it to be. And so this is the perpendicular bisector between the point 3 on the real axis and the point 3i on the imaginary axis. So I can join those up with a dotted line. But the perpendicular bisector here will go through the middle of that because it's symmetrical, so it's 3 and 3. It will go through the origin. It's got a gradient 4. And these are the hardest ones, I think, to work out which side you want to shade. So I've got a greater than or equal to sign, so I do need a solid line like we've just drawn in. You've got to decide then what this means. So what this is saying, this side is saying, is these are the complex numbers where the distance, or the distance of the complex numbers from 3. This right-hand side is saying the distance of the complex numbers from 3i. So the whole thing is saying what's I want the complex numbers where the distance from 3 is bigger than the distance from 3i. Okay. Or I want the complex numbers that are closer to 3i. So it's this side that I want. if you are unsure, you can test a point. So the origin is usually good to test, but we can't test it this time because it goes through the origin. So I'm going to pick z equals 3, that point over there on the right hand side. Okay. So if I put z equals 3 on the left hand side, I've got modulus of 3 minus 3, which equals 0. On the right hand side, I've got modulus of 3 minus 3i, which you can work out, which will give you 3 root 2. Obviously, 3 root 2 is bigger than 0. That doesn't fit in this inequality here. So from our test, 3 is not in the region, and we want the other side. There are 3 U-tries. Please pause the video, have a go at those 3, and in a couple of seconds, I'm going to reveal the answer. So for this one, should be a dotted line because it's a strict inequality. It's a circle centered on 3i on the imaginary axis and radius 2, so it doesn't cross the x-axis. We want the region where the distance of the complex numbers from 3i is less than 2, so that's the inside of the circle. For this one, so we're starting at 3 on the imaginary axis. We've got an argument of minus pi over 4, so going below the horizontal pi over 4 is 45, and then shading the region in between 0 and minus pi over 4. So put a solid line along the horizontal as well. I want the region in between those two there. Finally, for this perpendicular bisector, so it's perpendicular bisector between 3 and minus 3i minus 2i. So it's a horizontal line across at 0.5. The region where it's satisfying this inequality is the points that are closer to minus 2 than 3. So the distance of the points from minus 2i is less than the distance of the points from 3i. So the ones that are closer to minus 2, which is the bottom half of this line. If you weren't sure, you could test the origin in here and you'd get 2 is less than 3, which is correct. So you want that bottom bit. Again, a common thing for you to do is to represent multiple inequalities on an eigendiagonal and have to work out other bits. So first off, we've got 2 loci here that we've been asked to sketch. First one is a circle, needs rewriting z minus 3 minus 4i plus 5. And the second one is a perpendicular bisector, which doesn't need rewriting. It's perpendicular bisector between 0, between the origin and 6 on the real axis. So let's draw our circle first. So it's at 3 minus 4i, something like this. And it's got radius 5. What you should be spotting here is that we've got a 3, 4, 5 triangle. If we work out the distance of this point from the origin, it is 5. So this circle will be going through the origin. Do be on the lookout for that. We've got, later on, we've got less than or equal to inequality. So we do want a solid line for this circle. Something like that. Then for the perpendicular bisectors, it's a perpendicular bisector between 0 and 6. So 6 on the real axis is here. Now, it turns out that this circle will go through the real axis at 6, and we can tell that because of the symmetry of the circle. So we've got the center x coordinate is 3. That means that the points where it crosses the x-axis should be symmetrical either side of it. So because it goes through the origin, I know also it will go through at 6. A perpendicular bisector then will go through the center of this circle, so it goes down through 3. That is a solid line again because it's strict. It's less than or equal to inequality. It then asks us to indicate by shading the region of the eigendiagonal which satisfies those 2 things here. So first off, for the circle, we want the inside of the circle because it's all the complex numbers where the distance from the center is less than or equal to 5. So that's inside. You then got to decide which half you want for the perpendicular bisector. So this is saying it wants the points that are closer to the origin than to 6. The distance of, or the modulus of z, the distance from the origin of these points is less than the distance from 6. So the points that are closest to the origin, which is the left-hand half of this. Again, if you were unsure, you can test a point. So you could test 0, 0 in this, and you'd get 0 on the left-hand side, you get 6 on the right-hand side, which is correct. Please pause the video and have a go at the U-try, and I'll reveal the answer in a couple of seconds. So for this one, you've got a circle centered on 3 with radius 3, so it does go through the origin again. You've got a half line starting at 1, making an angle pi over 4 with the positive horizontal. The mod z minus 3 less than or equal to 3 is the inside of the circle. The argument 1 is between 0 and pi over 4, so it's that kind of wedge shape in there. It's not a sector, it's just a wedge shape area. We're now going to move on to solving some harder loci problems, which again, they do like to ask things like this in the exam. So first off, we're being asked to draw this locus satisfying this. So we recognise this as a circle because it's got a modulus on one side and a number on the other side. It does need rewriting as z minus a complex number like this. So we know this is a circle centred on 2 minus 1. And with a radius of 4, so that will go past the origin. If you work out the distance of the point to the origin at the root 5, so 4 goes beyond that. So again, using your compasses to draw this. Or something like that. I'm not going to label up an intersection with the axes because they're not straightforward. It then asks us to find the maximum minimum values of modulus of z for points on this locus. So what this is saying is that all of these points on the circle, we can call z. So z is just any one of these points on the circle here. It's asking for the 2 points on the circle, one which is the furthest away from the origin and one which is the closest from the origin. So hopefully kind of intuitively, you can see that this point over here is the one that's the furthest away from the origin. This is the maximum value of z, modulus of z. And it turns out that this line, joining up the maximum value of z, the furthest one away, will always go through the center of the circle. So that sort of makes sense too. So to work out the maximum value of this z, well, I know the distance from the origin to the center. We've worked that out using Pythagoras. 2 squared plus 1 squared square root is root 5. We also know the distance from the center to the maximum value of z, that's the radius of the circle, which is 4. So the maximum value of modulus of z is just 4 plus root 5. Similarly, hopefully intuitively, the one that is closest to the origin is this point over here. And again, if you think about the line from minimum value of z to the origin, this will be along the same line as the maximum value of z, so it lies along the line through the center. So to work out the minimum value of z, this green bit here, well, we know the distance from minimum value of z to the center is 4. If we take off that root 5, then it'll be left with that green bit. Minimum value of modulus of z is 4 minus root 5. More sketching this time. So first off, we've been asked to sketch this locus, doesn't need rewriting. So this is a circle centered on 2i here with a radius of 1. So a small circle won't go through the origin. Just like that. So up to 3 down to 1. Easy peasy wants us to find the greatest and least values of modulus of z. So the furthest away from the origin, maximum value of z, is along the line that goes, it's basically this point up here. This is the point furthest away from the origin. So this is just 3. You can see that there. I mean, you can work out as the distance from the origin to the center plus the radius. And the minimum value of modulus of z is just 1. That's the distance from the center to the origin. Take away the radius, which is but the interesting one this time is this argument 1. So it asks for the greatest and least values of arg z minus 1. Well, arg z minus 1 is a half line from the point 1 on the real axis. And it could be anything. It hasn't told us an argument, so it could be this one, could be this one, could be this one, could be this one, and so on. However, what you have to realize about this one is that z satisfies both of these loci. It satisfies the arg z minus 1 and satisfies the modulus of z minus 2i equals 1. So it has to touch this circle at some point. It could go here, go through here, here. There's all of these argument lines that could be there. Okay. It's asking us for the greatest and least values of the argument of z minus 1. So the biggest angle and the smallest angle that we make with the positive horizontal, which will be at these tangents to this circle here. Okay. So the vertical one, and it is actually vertical, I'll mention that in a sec. The vertical one will be the least value of arg z minus 1, and the other tangent will be the greatest value. Now look out for things like these in these questions. Usually something is in line with something else. Might be that it's in line with the center of the circle. This time, the point that we're taking it from, so point 1, is it in fact in line with the edge of the circle there, because we know this is radius 1. So this first tangent is actually vertical, does make a right angle, and we don't need to do any calculations with that. So the minimum value of arg z minus 1 from my diagram is pi over 2. The question is now, how do we work out the maximum value of argument z, which will take more work. So I'm going to make my diagram a little bit bigger so that we can see what's happening. And here we go. So we've got a bigger diagram here. Okay. What I want to do is I want to work out this angle in here, and if I can work that out, I can add that on to pi over 2 to get my entire obtuse angle in there. To do that, I'm going to make a right angle triangle. That's always what you want to aim to do. And I'm going to make a right angle triangle using information that I already know. So this is a right angle triangle here because I know that this tangent makes a right angle with this radius. I know the length of this radius here is 1. And I can calculate the length of the distance between the point 1 here and the center of the circle there as well, which will give you root 3. Okay, so I've done that as sorry, it's not root 3. So I'll do that as so yes, root 3. So I know this is a right angle triangle here. So I've got distance 1 here, I've got 2 here. So it's not root 3, it's root 5, sorry. It's the distance between that point 1, 0 and 0 and 2. I can then use trig to work out what this angle in here is, so I'll call it alpha. So I've got that sine alpha, because I've got the opposite and the hypotenuse. So sine alpha is opposite over hypotenuse 1 over root 5. And I can work out alpha in my calculator. That's sine root 5, 0.46. To work out this entire angle in here, then I've got 2 lots of alpha. This is symmetrical, so this one is also alpha. So the maximum value of argument minus 1 is pi over 2 plus 2 times 0.464. Plus 2. 2.50. Another common thing to do is to find points of intersection between two loci. So here we've got a circle and perpendicular bisector. we've got a circle with radius 5√2. Centered on the origin. Label the intersections with the axes. And I've got a perpendicular bisector between the point 1 on the real axis, and this needs to be right instead minus I, so between the point -1 on the imaginary axis. Something like this should go through the origin because it's symmetrical. So we're being asked to calculate the complex numbers which satisfy both of these, which is those 2 points there. And there probably are different ways that you can answer this question, but the most straightforward and versatile way of doing it is to calculate the Cartesian equations of these loci and then solve them simultaneously to find the point of intersection. Cartesian equation of the circle is x squared plus y squared equals 5√2 squared, which is 50. The equation of the straight line, you can do it in full, or you can just intuitively look at this one and go, well, this is symmetrical, goes through the origin, so this has got gradient -1 and goes through the origin, so it's y equals -x. You could do it in full by finding the midpoint, finding the gradient between 1 and -1, flipping it and changing the sign, but I'm just going to write that down. We can solve these simultaneously then, so we've got x squared plus -x squared equals 50. That's 2x squared equals 50, x squared equals 25, and I get 2 values for x. X is plus or minus 5, which I would expect because there's 2 points here, and they do look symmetrical. They are symmetrical. We can work out the corresponding values of y, which will be the same, just with the opposite signs because it's minus x. And we should write our answers as complex numbers, not as coordinates at the end. So x is the real part. So we'll have 5 minus 5i as one of them. And for the other one, we'll have -5 plus 5i. Check if that looks like it makes sense. So the right-hand one, we've got positive real and negative imaginary. So that's your 5 minus 5i. And for your top left one, we've got negative real, positive I, positive imaginary. That's got -5 plus 5i makes sense. Pause the video, have a go at the U try, and I'll reveal the answer in a sec. So you've got a circle centered on 4 minus 2i. So you can write, and radius 5√2. So you can write down the Cartesian equation of this. For your half line, remember you do tan of your angle, tan of your argument to find m, which just gives you 1 in this case. And it goes through the point 0.06, so you can stick that in and you get y equals 6. X minus 6. Note that that is only valid for x is less than 6. Looking at your diagram, it's to the left of that, so only at values x is less than 6 are valid. Solving these simultaneously, so I substituted in for y, and I've got x minus 4 squared plus x minus 4 squared. Either you can combine those together and simplify it nicely, or I've expanded it out here, got a quadratic which we've solved to get 2 values for x of 9 and -1. Only x is -1 is valid. X is 9 would correspond to this point over here, which is not a valid point because it's a half line, not a full line. So using x is -1, you can substitute that in and get y is -7. So your complex number is z is -1 -7. Final example. On the face of it, this looks like a perpendicular bisector because it's a modulus on either side of the equals sign. But notice the difference here is that there's a 2 on the right-hand side in front of there, which means it's not a perpendicular bisector. So we're going to do this algebraically and see what happens. So just like we did earlier on in the pack, we're going to let z equal x plus iy. 3 plus 2i. And on the right hand side, same thing. We're going to collect up our real and imaginary parts. X plus 3 is the real part. Imaginary, we've got y plus 2. And over here, x is my only real part, and y minus 1 for my imaginary part. We're going to work out the modulus of each of these complex numbers using Pythagoras. So I've got x plus 3 squared plus y plus 2 squared square rooted equals 2 times the square root of x squared plus y minus 1 square rooted. I'm going to square both sides. Don't forget to square the 2. And then we're going to expand all this out and simplify it down. So I'm going to run out of space, but hopefully your answer more than mine. So you get x squared plus 6, x plus 9, plus y squared plus 4y plus 4 equals 4x squared plus 4y squared minus 8y plus 4 if I remember times a lot by 4. Collecting up your like terms, so if we take everything over to the right hand side, I get 3x squared minus 6x. So that across, taking y across, I get 3y squared minus 12y, so it's taking those across. And then your numbers, so we've got 9 and 4, so the 4's cancel. And that number across using that. Right down here, just make it more space. So I'm going to divide everything through by 3 to make my life easier. So I've got x squared minus 2x, so y squared minus 4y. Minus 3 to 0. Now I can complete the square. On each of my x and y's. And collecting this up gives me x minus 1 squared plus y minus 2 squared equals 8. So we know that this actually is a circle, center 1, 2, and radius root 8 of 2 root 2.